All right, let's take a look at example 1.3.2. It says, in nature, many single-cell organisms, such as bacteria, reproduce by splitting in two so that one cell gives rise to 2, then 4, then 8, and so on, producing a geometric sequence. Suppose there were 3 bacteria originally present. Determine the general term that relates the number of bacteria to the doubling period of the bacteria. State the values for T1 and R in the geometric sequence produced. All right, so let's build a chart to take a look at this. So we've got our start value. We have 3 bacteria. That is our first term. Here's our second term after 1 doubling period. We have 6 bacteria, just doubled. Here's term 3 after 2 periods. We have 12 bacteria, and this pattern goes on. So let's take a look at what we know here. Here's term 1 is equal to 3. Our common ratio is equal to 2 because we're doubling it. And using our formula, the nth term is equal to our first term times our common ratio to n minus 1. Our formula for nth term would be 3 times 2 to the power of n minus 1. So if I wanted to figure out how many there are after 100 doubling periods. So after 100 doubling periods, so I'm going to put 100 up here. That will be term 101. I have to look for my 101st term. So I'm going to look for term 101 is equal to 3 times 2 to the power of 101 minus 1. So my 101st term is equal to 3 times 2 to the power of 100. That is a really big number. I think Desmos can figure it out. I'm just going to bring up Desmos on my calculator and type it in. 3 times 2 to the power of 100. That's equal to 3.8 times 10 to the 30th power. That's how many bacteria there would be after 100 doubling periods. Fortunately, bacteria die so that we don't get that many bacteria. Now, if we're going to graph this, here's our terms, and here's our nth term. First term's term 1, term 2, term 3. And we're going to go up by 5s here because it goes up pretty quick. So our first term is 3. 3 is right about here. Our second term is 6, not much higher than 5. But then our third term is 12. It's starting to go up. Our fourth term would then be 24. That would be way up here. You can see how this forms a curved line. This is called an exponential curve. All right, so what is important here is that you can analyze a geometric series, you can determine the nth term, and you can find an example of it. Let's take a look at the next example. 1.3.3. Suppose the smallest reduction a photocopier can make is 60% of the original. This is a percentage, 0.6. What is the shortest possible length after 8 reductions of a photograph? That is originally 42 centimeters long. All right, so let's make a chart. Term 1, this is our start length, and it's 42 centimeters. Term 2. This is after 1 reduction. We take 42 and we times it by 0.6. 42 times 0.6, and we get 25.2 centimeters. Term 3 is after 2 reductions. And we take our value and we times it by 0.6 again, 15.12. So let's write our formula for the general term. Well, we know that term 1 is equal to 42, and our common ratio is equal to 0.6. Since our common ratio is less than 1 and greater than 0, it is going to get smaller and smaller. So our general term is equal to our first term times our common ratio to the power of n minus 1. So our Tn is equal to 42 times 0.6 to the power of n minus 1. Now, we are looking for after 8 reductions. Now, after 2 reductions, that's term 3. So after 8 reductions will be term 9. So what we're looking for is term number 9 will be after 8 reductions. So we're looking for term number 9 is equal to 42 times 0.6 to the power of 9 minus 1. Now I can just put that into decimals. My calculator, 42 times 0.6 to the power of 8, and I will get 0.71. So about 71 millimeters. So for this one, we started at 42 centimeters. We reduced it by 60%. After 8 reductions, it will be 0.71 centimeters. Now, if we were to just quickly sketch a graph of this, term 1, 2, 3, 4, 5. So term 1 would be up here. Term 2 would be, term 2 would then be down here, down here. It would go like this. It would start to curve down like that. Now, I drew this line, but this data is not continuous data. It does not make sense to say term 1.5. We only have whole numbers for terms. I just draw this line to indicate the trend of the graph. Technically, it shouldn't be there. All right, so again, what's important? Turn the percent into a decimal. Analyze your geometric series. Figure out term 1 and common ratio. Formula for the general term. You can use that to solve for the problem.